Hello, everyone, and welcome to our presentation. My name is Janine Donnelly. I am the Manager of Webinars for IBM Systems Magazine, and I will be the moderator for today's event. We will be holding a Q&A session at the end of the webinar. You may ask a question at any time during the event by entering it in the Q&A panel. If you experience technical difficulties during the webinar, please use the Q&A panel to alert us, and someone will assist you. You may download a PDF version of the slide deck by clicking on the drop-down menu labeled Event Resources on the bottom left of your screen. Today's webinar, How Busy is Too Busy? Automating Your System for Maximum Throughput, is sponsored by Compuware. Our featured speakers today are John Baker and Selby Shanley. John has over 25 years in the IT industry as both a customer and consultant. John has assisted many of the world's largest data centers with their ZOS performance challenges and held subject area chair positions with CMG for storage, capacity planning, and Z Systems. John is the current chair of the mainframe track at CMG and is a popular speaker at Share and IBM conferences. Selby is the principal designer and developer of ThroughPut Manager automation and is the product team's subject matter expert. Selby is steeped in mainframe technology and is well known globally as a ZOS, JES2, and WLM expert. So what is utilization and why should we care? What exactly is too high? And what is an accurate measurement? Today, John and Selby delve into that topic and help you get busy, but not too busy. Without further ado, John, I'll turn the presentation over to you.
Thanks, Jean. Thanks, everyone, for joining. It's good to be back hosting another SysMag webinar. I always like you guys. Now, just a bit of housekeeping up front. For those in the audience who may be unaware, ThroughPut Manager is now part of Compuware. So welcome back to our loyal MVS audience, and we look forward to new questions and feedback from those of you joining us for the first time. Simple agenda today. First, we'll look at some of the common definitions of utilization and contrast those with what's happening in your mainframe. Then Selby will share some of his trade secrets of how we manage utilization with ThroughPut Manager. Lastly, we'll touch on the related aspects of balance and software costs. And as usual, we should have lots of time at the end for your questions and feedback. Okay, let's get going. Utilization is a simple enough word, but it can be interpreted in many different ways. Whether or not you're familiar with its actual definition, I can guarantee that utilization affects your life every day. So let's start by looking at a couple of definitions. Now, I've been working with the concept of utilization for most of my career, but everyone these days asks Google, so I figured I'd see what it has to say. This was not exactly what I expected at the top of the page. I suppose this helps explain why my old boss used to say a busy CPU is a happy CPU. That's a true statement. Are you there, Bruce? It struck me that quite a number of common definitions of utilization involve profit or business angles. Now, I'm not against these ideas by any stretch, but the general point I would make with Google is that the top answer is not necessarily the most accurate, it's the most popular, which is why people talk about what's trending, I suppose. But it's on the internet, so it must be true, right? In any event, this definition is not very helpful for us, so let's be a little more specific about what we're looking for. Now, this definition's a little better, but it's still missing a few key points, I think. Unless you're only talking about a single CPU during a single instant in time, you're dealing with averages. Average across CPUs and average across time. Almost every computer you encounter today has multiple CPU cores, and the most common RMF interval on most mainframes is 15 minutes. Now, another aspect that applies to computer systems is virtualization. You can have logical CPUs, which are just virtual entities, and physical CPUs, which represent the actual hardware. Now, this is important as many of the utilization values we see in reports today only represent the logical values. And as we'll see, that's not giving you the full picture. Okay, enough with the Internet. The widely known and respected Jonopedia, which you won't find on the Internet, defines utilization as follows: a measure of usage over time. I guess I'd expand on that to add that utilization is typically expressed as a percentage. Let's take these two light bulbs. Viewed in isolation, one could say that one is 0% busy and the other is 100% busy. Viewed together, we could say that the lights are collectively 50% busy. The question is, how often are you using them? That's the time aspect. If we use a measurement interval of 1 hour, what you want to know is how long out of the hour were the lights on or off. If they were on for 45 minutes, that would be expressed as 75% busy, 75% of the hour. Now you can have any number of lights, and you can have varying time intervals to really complicate things, but this is the basic concept of utilization. 80% busy just means 100% busy for 80% of the time. Now here's a real-world example using a box with 2 CPUs. In both cases, we're assuming a measurement interval of 900 seconds or 15 minutes. As I mentioned a minute ago, this is pretty common with RMF today. In the first scenario, one CPU is dispatched for the full 900 seconds, so it's reported as 100% busy. The second CPU is only dispatched for 450 seconds, so it's 50% busy. In scenario 2, both CPUs are dispatched for 675 seconds each. Therefore, each CPU is 75% busy. Now, consider that the average utilization that would be reported for this box would be 75% for both examples. Do you think the performance will be the same? Now, the universal answer, it depends. Yes, that applies here, of course. Time plays a big role. While we know the total dispatch times over the interval, we don't know the distribution of that time. That is to say, we don't know if the CPUs were on and off for alternating seconds, or on for several minutes, then off for several minutes, or any other random pattern. All we know is the accumulated time they were used within the 900-second interval. This is the importance of time in the calculation. The more frequent your sampling interval, the more accurate your measurements will be. As an aside, that's why strobe samples things very frequently. Now let's look at something you probably experience every day. You don't need to look further than your own laptop for examples of utilization. My wife uses a Mac, and she refers to it as the beach ball of death. This is a snapshot from my own laptop using Windows Task Manager. It reports the CPU usage of my PC as 15%. But how closely does that number match reality? Let's take a closer look. The 8 boxes on the right represent the 8 cores in my machine. The first one looks pretty busy. Peaks looks like around 90% or so. The next one's blank. Third one seems to peak around 80, followed by another blank one. And the remaining boxes, as you can see, kind of alternate around 30 or 40 and a couple of more blanks. So here we have an example where the number of CPUs is pretty important in the context of the reported utilization. If I'm only looking at one number, 15%, I don't have a very complete picture. I'll also let you in on a little secret. This machine only has 4 physical cores. The other 4 are virtual, which brings us to our next point. Now, to give you some perspective, we look at a lot of SMF data. The volume of data that I've analyzed over the year must surely have contributed to some great profits for the storage vendors. It takes up an awful lot of space. And I can tell you, LPAR dispatch is probably the most common delay that we see today. And it's also probably the least visible. In a nutshell, LPAR dispatch delay is the ratio of logical processor busy to physical processor busy. This is that hard reality where virtualization runs into the laws of physics, which are not so flexible. For example, you can get a Z13 with 141 general-purpose processors today. You could configure that box with 85 LPARs. Now, you could, in theory, then configure all 141 logical processors on each of those 85 LPARs. Now, let's just think about that for a second. That's almost 12,000 logical processors on a single box. That sounds massive, and I'm sure marketing loves it. But let's come back down to earth for a second. How well do you think that configuration is going to run? It's not going to run well at all. All that virtualization remains dependent on the finite capacity of those 141 physical cores. Kathy Walsh from the IBM Washington Systems Center, she coined the term short CPs over 10 years ago. And the point of her analysis was to explain at that time why CICS transactions would run poorly even though the average utilization might seem reasonable. This principle remains true today and applies to any workload. And this is what it looks like. Now there's three components to this chart. The blue bars represent the number of active initiators, which is effectively the number of concurrent jobs running in each time interval. The two lines represent two views into the utilization. The green line is the logical, MVS busy, and the red line is the physical, CPU busy, the cores that are servicing that LPAR. Viewed another way, the green line is the demand from the applications on the LPAR in the operating system. And the red line is the supply from the machine that Prism is delivering to the LPAR. Some of the time, the lines overlap, meaning demand is meeting supply and life is good. But when you see gaps, as you indicated here, this means that supply is unable to meet the demand. This is driven by demand from other LPARs, the CPU weight or the minimum share for each LPAR, and the available capacity of the machine. Now, as I mentioned at the beginning, I'm sure that most of us have experienced the effects of high utilization, even if we're not familiar with all these technical nuances. Some of us experience utilization every morning. High utilization simply means you're going to wait. You can let everyone on the highway, but then no one will get moving. And what if some of these were emergency vehicles trying to get to an accident? They can't get through. That's just like your critical applications. If the system is too busy, everything waits. Now this chart is basically the mathematical equivalent of the traffic jam in the previous page. It's a queuing model that shows what happens to a job or transaction with a simple execution time of 1, and as things get busy. At lower levels of utilization, you could double your load and likely not feel much of an effect on the overall response time. At high levels of utilization, however, a slight increase in load can push you over the edge. Then your system is basically gridlocked, like the previous slide. And there's a financial aspect to this as well. Running at extreme levels of utilization is very much like an inefficient furnace or a fireplace. So much of the heat is going up the chimney, but you're still paying for all that fuel. Now we're going to get back to cost later on. First, we want to share a few secrets about how we manage utilization with ThrouPut Manager. Now ThrouPut Manager is enterprise software. It's not an app. This is heavyweight stuff. So for the techies in the call, ThrouPut Manager tips the scales at around 2 million lines of mostly assembler code. That means it's very complex, but also extremely efficient. TM interfaces with JES2, Prism, and Workload Manager to stay up to date on the current state of the machine. And while its primary benefits are directed at batch, ThrouPut Manager has a positive effect on the performance of all applications. By effectively managing the utilization of the z/OS environment, all applications run better, not just batch. TM has been under constant development for almost 30 years, and while it can do many things, we're going to focus on the automation functions listed here today. And with that, I think I've made you wait long enough. I'm going to pass the mic over to Selby so he can give you a peek into how the intelligent automation in Throughput Manager works its magic.
Thanks, John. When managing utilization, TM automation has some clear goals. First of all, to run the most important work first. Every IT shop has bad days. Those days when hardware or software fails and the batch window shrinks due to an unscheduled outage or running for some time with reduced capacity. When this happens, it is vital to focus on delivering the most important work first to minimize the consequences of the failure or outage. This is difficult to do manually, particularly when operating under pressure. Secondly, for many installations, the batch window is getting tighter and tighter. If utilization is managed properly, job runtimes will decrease and job chains finish earlier. In a large system, both CPU demand and capacity can vary widely in a short time. While utilization management has to exploit available capacity, it must avoid and respond to overload conditions. Throughput Manager automation controls utilization on an individual LPAR basis by managing job selection and the deployment of initiators. In other words, Throughput Manager determines which jobs should run and how many should run at any given time on a particular LPAR. The input for these decisions comes from constant performance monitoring and analysis. System conditions change quickly, so Throughput Manager analyzes LPAR performance every 10 seconds. It takes input from Workload Manager and the CPC itself to build a detailed picture of a number of different metrics. The analysis information directly affects each job selection decision and the number of batch initiators. Why a 10-second cycle? Because that's how often Workload Manager provides new performance data. Throughput Manager considers a range of performance data in making its decisions. It tracks the overall CPU consumption of the CPC and each LPAR. Throughput Manager monitors the workload performance, evaluating delays and the performance index for each batch service class, and the amount of CPU available to the service class based on its Workload Manager importance level. John introduced the concept of LPAR dispatch delay when logical processors are waiting to run on physical processors, a delay that is not factored in a Workload Manager's calculations. However, it's important to consider, since when it is significant, workload may appear to be executing, but in fact may be barely running at all. Throughput Manager calculates the dispatch delay percentage on each LPAR. For those of you familiar with z/OS hyperdispatch, it takes that into account too. TM factors the effect of the dispatch delay into the actual delay being experienced by each service class to get a more accurate picture of actual service class performance. In a busy CPC, current CPU demand and available capacity can change rapidly, and these changes are often connected. For example, starting up online applications or other high-priority load significantly increases CPU demand on that LPAR and lowers the amount of CPU available to less important work, which is usually batch. This also affects the amount of CPU available to other LPARs on the same CPC. As an LPAR consumes more and more CPU, the amount of spare CPU is reduced. Of course, the reverse is also true. If the online work subsides on one LPAR, all other LPARs see an increase in available cycles. Soft capping and installation use of capacity on demand are two other events that cause sudden changes in capacity. Throughput Manager observes all of these changes and the effect on the currently executing batch workload. TM responds by modifying the number of currently executing batch jobs, reducing it if there is poor performance, or increasing it to take advantage of newly available capacity. Now let's look at how TM accomplishes the goals discussed earlier. To ensure that the most urgent work finishes first, Throughput Manager orders the execution queue, so the most urgent jobs are at the front of the line. In other words, at the top of the queue. In a Throughput Manager automation policy, the installation identifies all batch workloads and assigns a relative importance and defines the SLA, service level agreement, for each. The urgency of a particular job is determined by its importance and how long it has been in the queue. In other words, how's it doing versus its SLA? With jobs having different importance and SLAs, their relative urgency is constantly changing. TM reorders the queue every 10 seconds to ensure that the most urgent work is always first. All of this comes in very handy during one of those bad days. Throughput Manager delivers the critical work, taking a load off operations personnel during a stressful time. After having one such bad day, a customer told us, Throughput Manager did a better job getting the work out than we ever did manually. Throughput Manager automation controls job selection for all batch workload under TM control. At job selection time, TM assigns the Workload Manager service class to be used by the job. In order for a given job to be selected for execution, the service class must be performing acceptably. Because everything works better when you avoid overloading. There is no point in adding workload to a service class that is overloaded. It just makes the problem worse and slows down the other executing work. The other lever that Throughput Manager automation uses to limit how much work runs at once is automated initiator deployment. So the obvious question is, why not simply open up a big pool of initiators and control utilization just using job selection? After all, we'll stop once the performance gets bad, right? Well, it turns out that this isn't sufficient, and here's why. If many jobs get selected at once, it can take up to 10 seconds before Workload Manager realizes that service class performance is now terrible. If you have a large group of idle initiators and a large number of jobs become available for selection, by the time Workload Manager indicates that the performance is bad, it's simply too late. So Throughput Manager controls the number of initiators to provide optimal loading based on the current performance of the system and closely manages the number of idle initiators to avoid overloading. You can see from the slide that if the system has spare capacity and there is more work to run, TM will automatically open up more initiators. If the system is busy but not yet overloaded, TM will tend to leave the number of initiators alone. However, if there are high importance jobs in the queue ready to run, TM may still open up initiators to run those jobs. Finally, if the system is becoming overloaded due to changes in demand and/or capacity, TM will start reducing the number of initiators. And this all happens automatically without any operator intervention. It's not important when a batch job starts. It's when it ends that matters. This is particularly true for production applications, where jobs are usually dependent on the completion of others. Jobs end sooner in a TM-managed environment. We did a benchmark that shows this in action. We ran over 1,000 jobs being submitted over several hours. These jobs had a mix of CPU and I/O load and were run in Workload Manager batch initiators and under TM automation. There were no job dependencies. Of course, the two environments were identical in every way: hardware, software, and service class definitions. No other work was running on the CPC, so the total available resources were the same. The result? Throughput Manager automation ran far fewer jobs at once, started many fewer initiators, but completed much more work. Here's a graph of the benchmark results. You can see that the work ran for hours. Workload Manager started 300 initiators, while TM automation automatically started only 25 initiators. As the graph shows, after over 8 hours, TM had completed 200 more jobs. The only reason that number didn't get higher is that we stopped submitting work. These results will be even more dramatic with workloads that make use of job dependencies. Every so often, we repeat this benchmark and see the same results when comparing Throughput Manager automation against Workload Manager batch. Now, many installations use manually controlled just-to initiators. In that environment, you will often find that the machine is either overloaded or underutilized, since it's just not possible to be as effective manually as automation that is constantly monitoring the environment and making instant decisions. Sometimes less is more. By avoiding overloading, Throughput Manager automation gets more batch jobs done faster. As you can see from the picture, there are some distinct disadvantages to being out of balance. Let's see how Throughput Manager automation provides batch workload balancing at a JESPLEX. First, let's look at what balanced means. It's not simply making sure the same number of jobs are running on each system. Balanced means that each member of the JESPLEX is running the appropriate amount, the right amount of batch workload for the current conditions on each member, while still respecting any installation-imposed constraints on where a batch job can run. What do I mean by appropriate? First of all, the utilization and service class performance should be optimal. Obviously, there is no point in overloading one low-capacity LPAR just so it's running the same amount of load as a much larger capacity LPAR. And even if two LPARs have identical capacity, they may have much different workloads. If one of them has a heavy online load and the other does not, one LPAR has far fewer resources available to run batch workload than the other. A balanced distribution of workload should end up with both LPARs running as much as will still result in acceptable performance. Finally, Throughput Manager will obey any system affinities specified by the installation for certain jobs. As we've covered, TM controls the utilization on each LPAR. This, on its own, guarantees that batch workload will spread to other LPARs in the JESPLEX. When the CPCs are close to 100% busy, it gives close to optimal balance using this mechanism alone. TM makes certain that no individual LPAR is overloaded. When there is some available CPU, Throughput Manager takes specific actions to ensure that jobs don't all start on the same LPAR. Automated initiator deployment helps too, so that one LPAR doesn't start too much load at once. And utilization control helps to ensure that LPARs stay optimally loaded and don't go out of balance due to overloading. Now that you've got some inside information on how TM manages utilization and balances workloads, we're going to talk about how TM can also reduce monthly software costs. First, John is going to set the stage. John?
Thanks, Elby. I just love that horse picture. So we've been talking about utilization and its effects on performance. Utilization also has an effect on software costs. This is that age-old jousting match between capacity and finance, where capacity tells you what you need and finance tells you what you're getting. I've lived in that world for far too long. In case software costs aren't really your specialty, though, I'm going to give you a crash course here on subcapacity pricing. Now, subcapacity pricing is the method by which most mainframe sites are billed by IBM today. Rather than the old method where you were billed based on the total capacity of the hardware, subcapacity pricing is a consumption-based metric. That's a key point. It's not about the size of the machine. It's about how much of the capacity you use. Now, this table gives some insight into the values we're talking about. The actual numbers have been changed to protect the innocent, of course, but these are reasonably representative of a typical site today. The level refers to the available tiers in this pricing model. As your consumption gets higher, what we call the incremental rate gets lower. So as you can see, everyone pays pretty big up front, but enjoys, shall we say, volume discounts as you grow. Now, the range refers to the number of MSUs in each tier. MSU stands for millions of service units. Now, this term has no relationship to the service units used to measure your workload manager service classes. That's for another webinar. MSUs are the metric by which IBM measures and bills for your use and support of the major subsystems, such as, well, COS to start, DB2, CICS, and so on. Now, as you can see, each subsystem has a rate at each level, and that will be multiplied by the MSU consumption in a cumulative manner to arrive at your total monthly license charge. That's when you hear the term MLC. That's on the far right. So when you also hear the term 4-hour rolling average or rolling 4-hour average, apparently there's quite a fierce debate over which one of those is right. I assure you they are interchangeable. This is referring to the 4-hour rolling average of MSU consumption. That's what that value is. The peak value of the 4-hour rolling average determines your software bill for the month. So getting back to that capacity versus finance, the key to winning that jousting match is keeping your 4-hour rolling average low without hurting your application performance. Now, there's 3 traditional methods for dealing with the 4-hour rolling average. See, I want to say it both ways even. Soft capping, limiting capacity, or manual methods. Now, soft capping is relatively common. Lots of people doing that today. But it may have undesirable effects. The scope of a soft cap is an entire LPAR, so you don't have any guarantee that critical applications won't be affected when you're capping. Now, limiting capacity, on the other hand, is a bit of an old school, I'll call that a sledgehammer approach. So turning off engines simply limits the available capacity in the machine, thus limiting the maximum possible 4-hour rolling average as well. Now, the main drawback to this approach is that you will very likely find yourself running at very high levels of utilization, and I think we've shown already why that's not such a good idea. Lastly, there's the lost art of trying to manually control your consumption. I'll call this the console jockey approach. Now, I sympathize with that dedication because I was one once. But the reality is this method is just doomed from the start. Even the most brilliant technician simply can't analyze all of the statistics coming out of the machine. Combine that with all of the immediate business priorities and decide exactly how much to run, when, and where, and then repeat that process every 10 seconds. And we have to sleep as well. So I really think there's a better way. Now, automated capacity management isn't just a concept. It's a component within Throughput Manager. In addition to controlling when and how jobs run based on performance and utilization factors that Selby's talked about, ACM allows you to include financial variables. So within the TM policy, you can designate it which jobs are eligible for constraint based on 4-hour rolling average ranges. 2 points there. So rather than capping an entire LPAR based on a single value, I can isolate specific jobs, so I'm address-based scope rather than LPAR scope, and I can have a gradual effect rather than slamming on the brakes when I hit a single limit. I'm going to pass back to Selby so he can share a few more secrets.
Thanks, John. ACM monitors the 4-hour rolling average and recent CPU consumption and compares it against any existing limits set by the installation for the LPAR. IBM calls this defined capacity, and for an LPAR group if there is one. The installation can also define ACM LPAR sets subsets of the LPARs on each CPC, each with their own 4-hour rolling average limit. What does TM do with all of this information? First, it identifies which limit is closest to being exceeded, and then automatically implements installation-specified actions to constrain CPU demand. The installation can specify actions for different subsets of the batch workload at levels such as 85% of the limit, 90% of the limit, and so on. Batch CPU demand can be capped using one or both of the following actions: changing the service class and/or controlling the maximum number of executing jobs. As the 4-hour rolling average changes, different service classes or maximums can be implemented. ACM lowers demand by automatically constraining installation-specified batch workloads according to rules established by the installation. It defers the CPU consumption of low-priority workloads until the peak 4-hour rolling average has passed. ACM works with or without IBM soft capping mechanisms. Used with IBM's defined capacity or group capacity limits, it allows the installation to lower these limits, resulting in lower peaks reported on their SCRT report and savings on their software bill. Installations who do not wish to soft cap can use ACM LPAR sets to cap demand and lower the peak 4-hour rolling average. So now that we've been through all the nuts and bolts, John's going to guide you through what all of this technology can do for your installation. John?
Thanks, Selby. So let's take a look at some real results to illustrate what Selby's been talking about. These are actual before and after charts from a large bank running Throughput Manager. The blue bars represent the interval demand, and the red lines track the 4-hour rolling average. The high peaks mean both poor performance and high costs. Valleys and white space are wasted capacity. By tracking metrics every 10 seconds and making dynamic adjustments, we're effectively automating utilization. Throughput Manager dramatically reduces the software bill, which is the big win for finance. But I think the real story is not just the lower 4-hour rolling average peak or any particular piece. It's the way Throughput Manager moderates the entire load to produce consistent application performance and provides an environment that's able to absorb unexpected bursts at any time, which is really important with all the mobile stuff that's coming into the mainframe these days. Really, I just think every mainframe should run this smoothly. Okay, let's sum up. So what is utilization? Again, I'm trusting Jonopedia, but it's possible that I'm biased on that. It's a measure of usage over time. Now, high utilization means things run slowly, and it means that you're wasting money. Remember, you have to consider multiple components. In our case, we're talking about multiple CPUs. I haven't seen a CPU with just a single processor in it in forever. And the time interval affects measurement accuracy. So as Selby said, that's why we check every 10 seconds. It's no coincidence that that is also a workload manager policy adjustment interval every 10 seconds. What does Throughput Manager do? Well, it avoids high utilization by tracking numerous metrics at frequent intervals, not just utilization. If you really want to think about, the effects of high utilization, at the end of the day, it's, well, what is your user experience? Are you waiting too long for what you're trying to do? That's why we want to track the actual velocities of the workloads, the actual delays being experienced by the workloads, not just the utilization in isolation. Throughput Manager also balances load across systems. You may have many machines, many LPARs. It makes sense to keep them balanced for all applications. Throughput Manager automatically responds to environmental changes. You could maybe turn on engines or turn them off. You would expect that your automation would respond to that, or unexpected things like a burst of workload. And of course, Throughput Manager is aware of the 4-hour rolling average and any caps if you use those. And what do these benefits deliver? Consistent performance from all applications. No, bursts that affect how things are running. You can't tell your customers, wait, don't come crashing our website right now because we're too busy. They're going to do it whenever they want to, and you need your system to be able to respond anytime. This is a 24-hour world we live in. Jobs finish sooner, and most important, work gets done first. As Selby said, do you actually care when a job started? If you have a 7 a.m. deadline, for all you care, a job could start at 6:55 or 3 days ago, as long as it's done by that 7 a.m. deadline. Appropriate loading as conditions change. Again, those bad days, things happen, things break, things fail. Subsystems fail, machines fail, stuff like that. Suddenly you don't have the capacity that you're used to having. When you've got tons of capacity, you don't need to worry about most of this stuff. Everything will run just fine. But when you're busy and you have a queue, then it's critical that the automation will adjust automatically. And of course, finally, last but not least, lower software costs. This is the big hitter in the data center. And obviously, it's typically the easiest return on investment for Throughput Manager as well. So, and speaking of that, if you are curious about how much Throughput Manager can improve your environment, send us an SMF data sample. God knows I have not looked at enough SMF data in my life, so please send more. I mean that sincerely, actually. We can analyze your workloads. We can analyze your MLC costs. We can provide an overview of potential improvements on many levels. And most importantly, how soon your return on investment could be. Now at this point, I'm going to pass the mic back to Janine, and we're happy to take your questions.
Thanks, John. Okay, now you'll notice that we have launched a survey. Please take a moment while we take your questions to answer the survey questions and hit submit. Thanks so much. Okay, John, first question. This is a good one with a little bit of detail here. I'm analyzing our recent 4-hour peaks, looking for what Throughput Manager might help us with. Since Throughput Manager is forward-looking, what time period would you recommend I look at? And then there's an example. For example, our most recent 4-hour peak was Monday from 11 to 1500. I assume I should look at those peak hours plus an hour or two before.
So let me give a short answer, and then Selby might elaborate. The question raised is actually a very important point. When you're looking at a 4-hour peak, a 4-hour rolling average peak, you don't just want to look at that individual hour. The 4-hour rolling average, by definition, is 4 hours of workload. In other words, the 4 hours that led up to that individual peak that you are billed for. All of the workload that ran in the 4 hours leading up to that workload should be considered. So your assumption is a good one. You definitely should look at that time frame, including a few hours before and after. Do you have some white space that you can defer things to and look at the relative importance level? And as Selby said, it doesn't have to be binary. You run or you don't run. We have the ability with automated capacity management to be gradual in the way we slow things down. Selby, you got anything to add there?
Yeah, I would look. It's hard to tell precisely from the question, but if the peak was really hit at 11 o'clock, obviously you should start easily 4 hours before that. And then, as John said, after the 1500 time, have a look and see how quickly it starts dropping off. It may even start the 4-hour rolling average may even start dropping off after that, before that rather, because the 4-hour rolling can continue to climb, but the actual usage is dropping. And that indicates more white space when we can actually run work, because Throughput Manager really wants to get that deferred work going again automatically as soon as it can.
Okay.
Now, and John, you can certainly expand on this a bit, but our analysis software actually will look at a whole month's worth of data and give a picture and show exactly what all the peaks are. In fact, we look at the top 50 hours in the month to see what the patterns are and see how much batch workload is contributing to those peaks. Janine.
Thanks. Is there any overhead caused by Throughput Manager running?
Great question. I mean, as we mentioned, Throughput Manager is written mostly in assembler, so it's extremely efficient, but I'm not just going to give you a general answer, because I have measured this. I have looked at the Type 30 records for the Throughput Manager started task when running some workload actually on a customer system. And just to give you a perspective, of course it will vary based on the load, but what I saw at that time was 0.003 seconds of CPU over a 15-minute interval. I'm not going to do the math on what percentage that is. It's very tiny.
I would also add that Throughput Manager, the algorithms in it are written to scale well, so that if you have a large queue or a small queue, a big machine, a small machine, there's no curve to that, upward curve to that utilization.
Great. Next question. What SMF records do you analyze, and how long a period?
So Selby touched on that a minute ago. Generally, we will ask for your SMF 70 and 72 records, and for a month. And the reason for that, in a nutshell, the 70 tells us the 4-hour rolling average. It's a variable that's in there. We get that number then for each LPAR as well as the entire machine. And the 72s allows us to correlate that with the actual workloads, batch specifically, but also other workloads, so we could see how much the workloads are contributing to that. And the reason for the month, Selby was elaborating a bit on that, is simply because if you lower a given peak, let's even just say for argument's sake, you cut a peak down to 0, and that peak was, let's say, arbitrarily 500 MSUs. Could you logically, realistically, and reasonably declare that you've saved 500 MSUs? Absolutely not. Because when is the next peak? The next peak might be 498 on a completely different day or a different hour, which means we've reduced it by 2. So then you got to go to the next peak and perform the same level of analysis to see how much you can reduce it. That's why, as Selby said, we go through the whole month looking at all of the peak hours to determine a realistic estimate.
Okay. Is it compatible for iSeries, also known as AS400, probably IBM I?
Sadly, no. We are ZOS only. I am a confessed mainframe bigot.
ZOS just 2, in fact.
Yes, to be specific.
Okay, next question. Does your cost analyzer product help me manage my year-end true-ups for MLC?
Oh, yes. The year-end true-ups, the hidden stuff. Yes, so if you've signed an IBM ELA, Enterprise License Agreement, you may be under the impression that you're covered and you're only going to pay X dollars. Of course, at the end of the year, they're going to look at what you consumed, and they're going to look at what your agreement is, and there may be some more money involved there. Obviously, I'm not privy to your agreements, but what I will say is that all of these models are based on consumption. At the end of the day, that's what the 4-hour rolling average is based on, and that's what subcapacity pricing is based on. And Throughput Manager ACM has the ability to reduce consumption. And just as an aside, because it is related, if you're considering moving to countrywide multiplex pricing, this is absolutely something you want to look at before you switch, if at all possible. Because if you're not familiar with the details of that, the big catch, as we call it, is that when you switch, your bill will be based on your last 3 months of SCRT levels. So you really want to do everything you can to lower those before you switch over.
Okay, what percent is the average dollar savings have you seen in terms of the average customer experience after the additional cost of the Throughput Manager software is factored in? Kind of an average savings. Average.
I can tell you, and I'm not in sales or marketing, but I've seen some pretty stunning numbers. We have some large customers that are saving millions, multiple millions. But you ask for average. Man, I hate to just say a number because somebody's going to hold me to it. Percentage average dollar savings. percentage average. I do know that typically the return on investment, because you do mention the cost of the software, which is absolutely fair, that the return on investment is typically within a year. Considering your average monthly license charge savings by using Throughput Manager automation, within a year you've got the price of the software paid for. And then, of course, you continue to save every month after that.
One of the things
Great.
that's also interesting is that a large mainframe with a lot of load obviously has the potential to save a lot of money. But the interesting thing that happens with smaller installations, they tend to be paying more for each MSU. That incremental rate is higher, so that they can still save a significant amount, even though the number of MSUs saved is smaller. The rate is very high, so the savings are larger than you might think, even for a small installation.
Okay. Is there any way to show the customer how much MIPS have been saved using Throughput Manager than before?
Oh, yeah. I mean, the same type of analysis that we would do in a before picture, we would do after. Your type 70, 72 records, of course, standard RMF records that you're cutting every day. And there shouldn't be any reason why we can't do a similar level of analysis after. The question mentions MIPS, which is really just a conversion. It's really just another metric of capacity, so we can express that in MIPS or MSUs. But the short answer is, yeah, sure.
Our batch workload is organized for the most part into the same service class. Would Throughput Manager benefit us?
Yeah, absolutely. I mean, there is the aspect of job importance that Selby talked about. So that particular piece may not be as applicable to your environment. But if you think about the automation of the initiators, the moderation of the load based on the capacity, what Throughput Manager is going to do in any environment is get the most work done in the shortest amount of time using the fewest resources. That's really the short answer. I don't know, Selby, do you want to expand?
Yeah, a little bit. It can still help load the service class up appropriately, and you can also still benefit that even though all of your or most of your batch workload is currently running in the same service class, that I bet you still have some jobs are more important than others. And in which case, the organization of the queue, the ordering of the queue to make sure the most important work gets selected first can help you a lot.
Okay. Do I have to add LPARs to use a subsystem optimizer?
Subsystem optimizer. I'm not familiar with subsystem optimizer. I think that might be applying to something else.
Okay. Let's go on to the next one.
But just in case there was some confusion, they were talking about Throughput Manager. No, you definitely don't need to add LPARs.
Okay, sounds good. Does the intelligent capping product require me to use main view?
No. Absolutely not.
Oh, wait a minute. Yeah. No. This is when you're just talking about intelligent capping. I think you're talking about BMC's product. In any rate.
Okay. Let's see. How can I tell when ACM has constrained the batch workloads, and likewise when those constraints are lifted?
ACM puts there's a couple of ways. First of all, every time a new level, an installation specified level, one of those 85%, 90%, 95% levels, or 100% is reached, it issues a message, and we do have people who are then using automated operators to trigger different actions that they want to take in addition to the automated actions taken by ACM. There are also commands. You can display it by commands, and we also put out SMF records at every 5 minutes on every LPAR to indicate all of the current numbers, what the 4-hour rolling average is, what the utilization in the last 5 minutes look like. If you have an LPAR group, we'll show what its 4-hour rolling average is, All of these details are in SMF, and you can analyze them, either take the SMF directly, or MXG also supports our SMF records.
Okay, can I use Throughput Manager with my existing caps? And if so, will it do any more?
Yep.
Yes, indeed.
Go ahead, Selby.
You can reduce them. And that's what we advocate people do, is start up with the ones you've got and use Throughput Manager ACM to reduce the batch demand, the demand from the low importance batch workload that doesn't have to run right then. And then start slowly decreasing your limits that you have, either defined capacity or LPAR group, and just keep reducing your caps and find the sweet spot in there. And that'll directly turn up in your SCRT, because the SCRT will say, bill this guy less.
Okay. Is Throughput Manager appropriate to a site that only has one production LPAR?
Oh, yeah.
Yes. Go ahead,
Selby.
I'll go ahead. After you, my dear Alphonse, yes. Yeah, absolutely. First of all, I'm not exactly sure what situation we're talking about, whether it's a machine with only one LPAR, which is a production LPAR, in which case, yes, you'll still find some amount of load, for example, that you could defer in the case of ACM. And of course, the automation still very much applies, because what we're trying to do is not overload the machine and get your production work out faster. If it's a production LPAR mixed in with test as well, you can use it to manage the test as well, leaving potentially more cycles available for production and have everything running better. And with ACM, you could, for example, defer the test load when the 4-hour rolling average is high, letting the production continue along.
Okay. Here's another question. What type of out-of-the-box, I quote, policies are provided?
Well, what we generally recommend people start with is we call a quick start policy, which essentially says, very likely today, you're running your batch in various input classes, class A, B, C, and so on. And we can very easily adopt that policy that says, okay, everything in class A goes into this service group, everything in class B goes into that service group, and so on. And you can use a very easy phased-in approach where initially Throughput Manager is in what we call passive mode, where it's not doing anything. And then you can gradually say, all right, now I just want you to start managing stuff that comes into Class A, turn that on with a command. Now I want you to manage Class B, Class C, turn those on with a command. If I want to turn them off, turn them off. And same with ACM. Initially, you can turn that on passively, so it will track the 4-hour rolling average for your individual LPARs, your sets of LPARs, and so on, but not take any action. And then you can gradually phase in workload that you want to defer.
Yeah, Throughput Manager policies are not nearly as complicated as Workload Manager policies. For example, I'm thinking particularly of the classification section in the Workload Manager policy. It's nowhere near that complex.
Okay, great. Unfortunately, that's all we have time for today. If you submitted a question and we did not get to it, just know that someone will reach out to you via email to answer your question. And I want to thank everyone for your participation and all the great questions today. I also want to thank both John and Selby for sharing their expertise with us today. Later this week, you will receive a follow-up email with a link to a recording of today's webinar, and that will go to everyone who registered. That concludes our webinar. Thanks again for joining us, and have a great day. Okay, we're